So we back. So I think we got one more person that needs to take the exam, and then we should have the results back before you leave for the spring break, definitely. All right. So today we're going to talk about chapter 3. All right. Any questions, concerns, or comments about anything? Nothing? Okay, good. All right, so today we're going to talk about chapter 3, momentum and energy. All right, momentum and energy. They are related. Okay, so we'll talk about momentum and impulse. We'll discuss a little bit about impulse being changes in momentum, right? That's what an impulse is. Conservation of momentum, energy and work, power, work energy theorem, conservation of energy, some simple machines, right? Like, I guess I'll give you some examples when we get to it. Efficiency, right? And that's probably related to those machines, how efficient those machines do work. And we'll talk about some sources of energy. All right, so what is momentum? Well, things that move, right, acquire momentum. And obviously, the more massive they are, the more momentum they will acquire, right? In addition to, if they move faster, they're going to acquire more energy as well, right? Or more momentum as well. So here's a formula for momentum, right? It's the product of mass and volume and velocity, right? That's what I just said, right? More massive means we get more momentum, right? Bigger, bolder, more momentum. Move faster, more speed, more momentum, okay? So obviously that equation is mass times volume, velocity, right? Of course, momentum is when we're talking about momentum, we normally use velocity, right, instead of speed. But for purposes of this class, I don't think we really need to get into that because that's not really important here. So we're just gonna skip that. All right. So again, that's what I was saying. High mass, high velocity gives you high momentum, right? Higher mass or higher velocity gives you higher momentum. High mass and low mass and low velocity give you low momentum, right? So the opposite is also true. And again, we'll save these for another day where we just focus on these questions. Right now, we're just gonna move through the slides, all right? Impulse. So impulse is a product of force and contact time, all right? So, of course, there's an equation for impulse, force times time, right? F times T. Greater force for longer time gives you larger impulse, right? Same force for shorter time gives you smaller impulse, okay? So those two are indirectly related, right? So longer time, larger impulse, shorter time, smaller impulse, right? Pretty straightforward. Okay, so here is an equation for the impulse. And change in momentum of an object is equal to the impulse applied to it, right? Which is force multiplied by the time interval, right? And that's what's shown here, right? Remember we said that the delta sign represents change, right? So the change in the speed or the velocity times the mass, right, is equal to impulse, which is force times t. So, momentum changes, right? Increasing momentum applied greater force for a longer time produces greater increase in momentum, right? So the examples they give are the golfer follows through while teeing off, right? It's the same principle with a lot of sports, right? Like baseball or something like that. That's why they tell you to follow through when you swing in a bat, right? Because you apply greater force for a longer time, right? And so it gives you more momentum, so it's more likely you will hit a home run, okay? So let's look at the cartoon here, right? When a car is out of control, it is better to hit a haystack than a concrete wall, right? Common sense, but with physics, but with a physics reason, right? So why is that the case, right? Well, according to the cartoon there, right? Is that what? In the case of the stack, right? The impulse is not going to be as much, right? Because the stack will not remain in the same spot as the wall will, right? So the impulse when the truck hits the wall is going to be greater and in the opposite direction, right? The impulse from the stack will be in the opposite direction, but it won't be as great, right? And the force from the truck, it will be greater. So that's why the truck will keep going, okay? But with the wall, obviously, the wall won't move, okay? Same is true for punching somebody, right? That's the difference from being punched by, a heavyweight person like Mike Tyson, right? And somebody who's less massive than Mike Tyson, like Floyd Mayweather or something, right? That's the difference. You're more likely to get knocked out by Mike Tyson from impulse because he's just more massive and he's following through, right? Meaning he's not tap, 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 right? And of course we've seen people break bricks and all of that kind of stuff before. Sometimes it can be fake, but it's possible, all right? It is possible. But we're not gonna get caught up in that, all right? But again, right, case of momentum changes, short time interval produces large force, right? So in the case where what we were just talking about, right? Well, Mike Tyson, his force is great and it's longer time interval because he's following through. So when he makes contact with your nose, he's gonna keep contact with your nose as long as he can, all right? But in this case, right, you can sort of create the same sort of effect, okay, but with a shorter time, by just however they break the brakes, right? So there's a concept, right, called conservation of momentum, right? In every case, the momentum of a system cannot change unless it is acted upon by external forces. The system will have the same momentum both before and after any interaction occurs. When the momentum does not change, we say it is conserved, right? That's why when you are driving in your car and you hit another car, right? Then that momentum that you had, right, gets converted into a lot of different forms of energy, right? That's why the car wreck is worse when you're traveling faster, right? Traveling faster, the car wreck is worse, right? So you get some heat, right? You get into a car wreck, two cars collide, you're gonna get some heat, you're gonna get some damage, right? In order for things to get damaged, right, there has to be some force, some energy somewhere to damage those things, right? And that energy is coming from your momentum, right? But anyway, the fact that it's conserved explains why, right? If we're traveling faster, then we get into a worse car accident and we're more likely to perish, right? Same is true for riding in an airplane, right? So, law of conservation of momentum: in the absence of any external force, the momentum of a system remains unchanged, right? So, total momentum before must equal to the total momentum afterwards, all right? And so that's very much similar to, and I know a lot of us have heard the saying what? That energy is never what? Created nor destroyed. It's conserved. It never goes anywhere. Only gets converted into different forms of energy. And heat is one of those forms, right? Although heat is useless for us a lot of times. In many cases. Sometimes it's good, right? Sometimes we can capture the heat and use it for things, right? Like warmth. But many times when things heat up, like when you're driving along the highway and you're sitting at the light and your car is on, your car is burning gas, your car is hot, and your car is burning energy. That's why you have the little flames. If you look to the car next to you when you're sitting at the light, it looks like it has little flames coming off the hood, right? Or little ripples coming off of the hood. It's heat, right? And a lot of times that's your gas, right? And that results in about maybe 30% of consumption, right? 70% of your gas is wasted in heat. It's you sitting at the light, other various things, right? So for every gas tank you buy, you probably get about 30% of that. All right, so that leads us to the discussion about collisions, right? Because that's what we were just talking about, right? When two cars collide, a car wreck, right? And so that's a physical principle, right? A collision, okay? And we have two types of collisions. We have elastic collisions and inelastic collisions, all right? So, in the case of an elastic collision, it's defined as a collision whereupon objects collide without permanent deformation or the generation of heat. Right? That's an elastic collision. Can anybody think of an example of an elastic collision?
Like a cattle?
A collision, though. A collision. I know that's good. That's good. I know where you're headed because you see the elastic, right? But a collision. Think about a collision. Two things hitting each other. Yes, that's it. That's good, but I wasn't expecting one that deep, right? Pool balls, right? Billiards. A pool ball. When two pool balls hit each other, they don't deform like two cars when they crash. When two cars crash, they bend up. You get heat. You get everything, right? But when two pool balls hit, right? In some cases, if you have the correct what they call it English or whatever, right? Then you can take a cue ball and hit the 8 ball, and the cue ball can completely stop where the 8 ball was, and then the 8 ball roll. So what happened in that case? That means that the cue ball transferred all of its energy to the 8 ball. So that means that momentum was conserved. No heat, no energy was lost. That's why they say that's why you shouldn't hit the cue ball so hard. Right? You gotta hit it because it's gonna transfer all of its energy because of what it's made of, the materials that it's made of. Right? It's like an incompressible solid. So it's not gonna deform at all. All right? So that's an elastic collision. The elastic balls bounce. That's a good way to remember it, right? That's why you was thinking about a rubber band, but that's good. Elastic, a rubber band is elastic, yes. Right? If you stretch a rubber band, although when you stretch a rubber band, right, it has a certain point, you can't stretch beyond, and it'll do what? Pop, right? But in most cases, if you don't stretch it too far, right, then it does what? It'll stretch and then come back to its original position. Right? So when you're stretching it, you're storing energy inside of it. Right? And you let it go, that energy is going to be released and it's going to bring it back to its original position or original shape or whatever it is. Okay? But now we're talking about collisions though. Okay? Right? So we just look here, right? See this one? And we just look at it, right? In this case, the green ball is moving. The yellow ball is sitting still. Green ball collides with the yellow ball. Now the green ball stops. The yellow ball is moving at the same rate that the green ball was moving. That's why these three are the same. You see that? Right? Look at this collision. This was what? One moving, one sitting still. This was two moving at each other. See that? They moving at each other, bam, they hit, then they go back out in opposite direction, same way, same speed. That's pool balls. That's an elastic collision. That wouldn't happen with a car, right? Two cars hit like that, they're not going back in there like that. All right? Same here. Okay. And I guess they just going through showing you what I just showed you. All right, so let's just move to the inelastic collision, right? So the inelastic collision is one where colliding objects become tangled or coupled together, generating heat, right? Inelastic collisions are often sticky, right? Now, can anybody think of an example of an inelastic collision? Anybody? Huh? Where two things collide, two objects collide, and after they collide, they normally just do what? Stick together. What have we been talking about?
Was that car wreck?
A car wreck. Yeah, a car wreck. That is an inelastic collision. All right? So, you know, depends on how you look at it, right? Whether the two cars are hit head on, whether one is sitting still and the other one is moving and that one hits the other one, right? However you slice it, the cars are gonna stick together after they collide. And if they don't stick together, then they're not gonna just bounce off each other and everybody's fine after that. Like billiard balls. That's an inelastic collision. Okay? So work, right? Now we're talking about work. Work is defined as the product of a force extended of a force exerted on an object and the distance the object moves, right? So in order to do work, right, the object must move. Okay? Because the equation for work is force times distance. Right? Force times distance. It's the equation for work. All right, so two things enter where work is done. Application of a force, movement of something by that force, right? So work done on the barbell is the average force multiplied by the distance through which the barbell is lifted, okay? So, in order to do work, that means that the object must move, right? So if we're lifting something that's too heavy for us and we're not able to move it, right? And we just, say for instance, we were on, what do they call it? The bench. Weight bench, right? And we tried to move the weights and they didn't move. Did we do work? Why not? Huh? I mean, we struggled. I mean, I struggled there and I broke out sweating and all kind of stuff. But so why didn't I do work? Because it didn't move, right? As simple as that. So no work was done. Okay? Right? So work is done against another force, or work is done to change the speed of an object. Right? So what happened in that case? That we did the work on the weights, right? Or we said we didn't do work because it didn't move, right? But we exerted effort. We broke out in a sweat. What happened?
Change the speed of the weights.
Well, no, but what? The work that we did was what? Not enough against the work that was what? Done by what?
The weights.
Which is Gravity, right? Gravity is always doing work. Well, if the weights weren't on the bench, they didn't have anything to hold them up, then what would happen to them? They would come crashing towards the earth, right? That's because gravity. Gravity will do work on those weights. It will move them to the earth. But because they're sitting on a rack, they don't move. But when you, as an individual, come to lift the weights, right, you have to do enough work against gravity, right? It's not that you didn't do any work, you didn't do enough. But you didn't do enough to move it, right? And so all of these things are intertwined, right, and related, right? Because if you think about it, right, when you wake up in the morning, right, in order for you to move from where you woke up to here today in class, you had to do work. You had to do work to get here, right? And so in the process of doing that work, you had to expend some energy, right? Because really, work and energy are measured in the same unit, which means they are very similar, right? It's the reason why we want to go in the elevator as opposed to climbing the stairs. Why?
Exerting less energy.
Huh?
Exerting less energy.
Yes, right? It takes less energy to get from first floor to third floor in an elevator than it does to climb the stairs. Right? Why though? Because, right, we said that what? Momentum is conserved. Right? So the energy that I had on first floor got to be the energy I'm going to have on the second floor. Right? We're talking about conservation of energy, but conservation of momentum, all of this is related. Right? Why? What energy, where did that energy go? Right? That I used to climb the stairs. Right? Right? Because I had to, in order for me to get from floor 1 to floor 2, right? Or 3, whatever it is, whatever I said, right? I got to do the same amount of work. Whether I go in the elevator or I go in the stairs, I climb the stairs. Same amount of work has to be done. So if it was easier, if I exerted less energy, right, in the elevator, as you correctly said, then what happened to that energy that I saved, right? Which was converted to work, right? It had to be, because it's the same work. Same work I used from ride the elevator to climb the stairs, right? And I'm just gonna make it easy for you, okay? Or I shouldn't say that. I should say I'm just gonna tell you, all right? So the elevator is doing the work. That's what I was getting at, all right? So in one case, you do the work, climbing the stairs. That's why if you maybe you didn't eat something this morning and maybe you don't have so much energy and you get up and you climb the stairs, it's a little different from getting in the elevator and going through the elevator, because the elevator is doing work for you, right? And I'm assuming we're gonna get to that when we start talking about machines, right? But back to this, energy, right, is basically synonymous with work, right? And so power is a measure of how much work I do over a time interval. Right? How much work I do over a time interval. Right? Right? So, when we say something is very powerful, that's what we mean. We mean it can do a lot of work over a short time interval. Right? Like I said, we're gonna go through all of these questions. We're gonna do that all on one day, and just focus on the clicker questions. All right. So work energy theorem, right? So again, like I said, work and energy are very synonymous. Okay, they are related. Just like I said. All right. In order for you to do work, you need energy. Right? Just that simple. In order for you to do work, you need some energy. Okay? And there's an equation, right, for calculating energy, right? And we know that to be 1/2 mv squared. Okay, that's pretty common equation. Okay, for kinetic energy. So, but what it equates to is what? Small changes in speed lead to large changes in energy, right? And that's because you have the square on the speed right here, or on the velocity. So when you put a square on it, you know, things you put a square, you square it, it doesn't take much. As it increases, this number rapidly increases, right? 2 squared is 4, 3 squared is 9, 4 squared is 16. You can see how it's rapidly increasing, right? All right. So, conservation of energy, right? So we talked about conservation of momentum first. Now we're talking about conservation of energy. And it's very similar, right? So energy just what I said earlier, right? We never lose energy. Energy transforms from one to another one, right? We never lose the energy, okay? And so you see the little cartoon right here. Right here, the object has the most kinetic energy and the least amount of, the most potential energy and the least kinetic. Why? Because kinetic energy, it has to be what? In order to have kinetic energy, it has to be what? Moving. So its speed here, or velocity here, is 0. So it has all potential energy, right? And so this is sort of similar, like if anybody ever been on top of a tall building or something like that, and you looked over the side of the building and you felt like something was pulling you over, that is literally the earth pulling you towards the earth, right? So that's where you have all potential energy. But after I cut the string, right, then that potential energy starts to convert itself to what? Kinetic. until I have maximum kinetic energy right here, and that's what I use to strike the post there. Alright? So machines, right? Principle of a machine is conservation of energy concept, right? Work input gotta equal work output, right? So, right? So we want to, so the input force times input distance has to equal output force times output distance, right? So this is, the principle of simple machines, right? And let's look at some examples. Let's see. Comparison of kinetic energy and momentum, right? So both depend on mass, velocity, momentum depends on mass and velocity, kinetic energy depends on mass and the square. All right, so that's just math, okay? So we have two principles, right? Conservation of energy and conservation of momentum, right? Momentum is M times V, right? That means what? Momentum before has some equal momentum afterwards, right? M times V, and energy, right? Which is kinetic energy plus potential energy, okay? And that's 1/2 mv squared, and potential energy is mgh, okay? But we're gonna go back through it, all right? So don't be alarmed if you are, all right? So it says momentum is a vector quantity, kinetic energy is a scalar quantity. So here, what that means is momentum depends on the direction, okay? Kinetic energy doesn't depend on direction, okay? So, again, we're gonna go through that and deal with some specific examples, okay? So, conservation, right? What does it mean to conserve, right? Conserve means to save, right? In the absence of external, so law of conservation of energy, in the absence of external work, input, or output, the energy of a system remains unchanged. Energy cannot be created or destroyed, okay? So, again, in those two examples earlier about climbing the stairs in one case, taking the elevator in the other case, right? The amount of work doesn't change from one example to the other one. It's just that the elevator does work for you by taking you up to third floor. Okay. Conservation of energy is consider the system of a bow and arrow in the drawing. I don't know about all this. When the bowstring is released, most of the temperature energy. Okay. All right, so that's for that. So now we get to machines, right? A device for multiplying force or changing the direction of force. Okay, no machine can put out more energy than is put into it. Right? So that means that it will have done what? Created energy. And we just said energy cannot be created or destroyed. Right? So it can only transform or transfer energy. Okay? So let's look at an example, right? And we all know this example as a what? This is a what? What we call that? Like a seesaw, huh? Like I guess you could call it a balance beam, but I don't know, no, it's more like a seesaw, right? Or what they call a lever, right? And we look, right? And we all know about the seesaw, right? You got a heavy kid and a light kid on the seesaw. What has to happen? Huh?
The kids are in the bottom.
Huh?
The heavy kids are the bottom.
I can speak up a little bit, I
The
can't hear you.
heavier kids are go to the bottom. Like, go down. Right.
Right, or the heavier kid sits closer to the fulcrum, right? The center, the heavier kid. Because remember, the lighter kid does what? In order to balance off with the heavier kid, the lighter kid has to do what? Go out further. If the lighter kid goes out far enough, then he's going to do the same work as the heavier kid who's sitting closer to the fulcrum. Right? So that's a lever, right? That's our seesaw. That's what we get from a seesaw. That's what, right? So efficiency, right? Efficiency is just how effective a device transforms or transfers energy, right? And then we hear, especially nowadays, we hear a lot about energy efficiency and all of that stuff, right? So in the case of light bulbs, right? Can anybody tell me what is the reason why we want to switch all of our light bulbs to LEDs? Why?
Because the heat preserve more energy.
No, you said it right the first thing you said.
Preserve.
What was the first thing you said? Or whoever that was, heat, right? Because heat, remember we said what heat was. Heat is a form of energy, but what is it? What can we do with heat in most cases? Huh? In most cases, heat is useless. That's why when you sitting at this is what I told you, when you're sitting in the car at the light and you look to the side and you see the heat coming off the other person's car. Can't do nothing with that. Once it burns, it's gone. That's why you're only using 30% of your fuel in your tank. That's why now the electric car does what when it gets to the light?
Stop.
It cuts off. Because you use most of your energy idling at the light. That's where you waste most of your gas. Okay? But it's heat. Whoever said that, heat, right? An LED does not get hot. Gives you light, very bright light, but it does not get hot. Which makes it last longer, which gives it a whole bunch of, an array of applications. Just for that reason, it does not get hot. That process alone, right, makes it efficient. Okay? And you see here, some energy is always dissipated as heat, which means that no machine is ever 100% efficient, right? So again, even though LEDs are great, much better than a incandescent light bulb, right? It's still not 100% efficient. No machine is 100% efficient. All right? So, of course, that leads us to a discussion of, well, where does the energy come from? And we are very familiar with that, being mostly Louisiana folks, right? The energy comes from underneath the earth, right? Or underneath the crust of the earth. Okay? That's where a lot of it comes from. A lot of the dirty energy, right? That's where it comes from. And it's a lot of different processes that we have to use to get to the energy that are very harmful to the environment, okay? But it is what it is, and we have to come up with alternatives, right? That's why we have alternative energy forms like solar, wind, all those different things, okay? Here's some examples right here, right? Photovoltaic panels, that's solar panel. Hydroelectric turbines, right? That's the dam. That's the dam with the big turbines on the dam, right? Wind turbines, right? It's like in the Midwest. And bio-based fuels, right? That's like cooking oil, making fuel from cooking oil. That's one of them, right? Or from any kind of biomass, you can make a fuel. All right, so, and of course, I was just talking about making fuels, right? Can be created from bio-based products, blah, blah, blah. Hydrogen, right? And if you're a person who stays abreast with politics and that kind of thing, then you've heard the president talk about hydrogen before. And hydrogen will be the next fuel that will go inside your vehicle, right? You will not use gasoline. Maybe you, maybe not me, maybe not you. Maybe you though. You will use hydrogen one day instead of gasoline, okay? And that's why it's so important for us to understand about hydrogen. Hydrogen is the most abundant element on the earth. We will never run out of hydrogen, ever. We will never run out. That's the problem with fossil fuels. We're gonna run out. So we have to find another fuel. And it's hydrogen. Okay? And we will never run out of it. All right? Here's some more alternatives. Solar panels, blah, blah, blah. All right, that's it.